Okay, let me explain what this means. Okay, we are considering a sequence of numbers, AI. Okay, so AI is a sequence of numbers. And this means, so this is called sum symbol or summation symbol, means summation of these terms starting from I equal to 1 and I equal to 2, so A2, A3, and so on, and up to I equal to 100. So this simply means summation, and that's it. And this I is the index here, starts from 1 and ends at 100. Okay, and that's it. By the way, why do we use this symbol? This is actually a Greek letter called sigma. And this is uppercase actually, and lowercase letter sigma is this one, which you might have seen in statistics. We usually use this symbol for representing a standard deviation. But for summation, we use this uppercase letter sigma. And sigma in Greek corresponds to S in Latin alphabet. And S stands for summation or sum. So that's why we use this sigma to represent a symbol for summation. Let's see some more examples. So what is this? I from 1 to 10, I. So I is an integer starting from 1 to 10. So this simply means 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. And that's it. And if you calculate this, you should get 55, I guess. And another example. What about I from 1 to 10 and 2I minus 1? What does this mean? So if you put I equal to 1, 2 times 1 minus 1, you get this. And if you put I equal to 2, you get 2 times 2 minus 1, and so on. And the last term should be 2 times 10 minus 1. Okay? So if you calculate this, this is 1, and this is 3. And actually, we get a sequence of odd numbers starting from 1, and that will be 5, and so on, up to that will be 19. And actually, this is, since this is just a summation, we can see the pattern here. So every term here, this one, so we multiply by 2 and subtract 1, right? So from here, we can factorize this 2 out. So 2, so this 2 out, and 1 plus 2 plus and so on, and up to 10. And we have minus 1 that appears 10 times. So minus 1 times 10. So because this minus 1 appears 10 times. So that is, so if you express this part as by the sum symbol, it becomes like this. And this one, negative 1 times 10, is actually 10 is, of course, maybe I should have written like 1 plus 1 plus and so on. So there are 10 ones here. So just 1, starting from 1 to 10. this sequence may not depend on I, but so this 10 becomes just this. So as you can see, you can factorize, split addition or subtraction inside this sum symbol into 2. So this one becomes 2i minus 1, and this part is this, and this part, so you can take this 2 out, and it becomes this. Okay. In general, if we have a sequence, let's say x ai plus y bi, we can split this summation into 2 parts, like n xai plus and ybi, and take x out. Since x doesn't depend on I, so we can take this out. And if this y does not depend on I, we can take this y out of the summation. Next, let's consider this type of summation. AI times, so the sum of AIs and sum of BIs. So what is this? Remember, each of these is a sum. Okay, so this is not equal to this. Now, this is a very common mistake, but this is wrong. Why? Because if you expand these summations, what we get is this: a1 plus a2 plus and so on up to an times b1, b2, bn. Okay, so if you expand this multiplication, so a1 times b1, a1 times b2, and so on, so a1 times bn, a1 times bn, plus a2 times b1, a2 times b2, times b2, and so on, a2 times bn. So this continues up to an times b1, an times b2, and so on, and an times bn. So here we have, in each row, we have n terms, okay? N terms. So in total, there will be n times n terms. However, consider this one. I from 1 to n, ai times bi. This means a1 times b1 plus a2 times b2 plus and so on up to an times bn. There are only n terms. Okay, so terms such as this or this or this, these are missing in this. So these sides are not equal. Okay, so don't get confused. So if you get lost, just try to expand and see what happens. Just always go back to the definition of the symbol. By the way, here I have used the index I here and index I here, but this I is not this I and this I. They are actually they are meaning the different things. In fact, these indexes or indices is just a temporary place for expressing the index. So we can actually use any other symbols for this. So this I is not, there's nothing special about this I. So we could have written instead J. So this means the same thing. You know, this I is just a placeholder for indexes. So whether we use I or J or something else, we could even use some Greek letter, for example, gamma, if you want to be exotic. So they all mean the same thing. Because, let's consider a concrete example. Consider this. Let's use some concrete examples. So let's say 5. So I from 1 to 5, this is just 1 plus 2 plus 3 plus 4 plus 5, right? So even if we use J, as long as this J is same as this J, it means the same thing. It means 1 plus 2 plus 3 plus 4 plus 5. So whatever letter you may choose, they always mean the same thing. So here we could have written I and J here. Maybe that would be less confusing. So these indexes signify different things. So in this, if you express this way, it is more difficult to get confused like this. Next, consider this double summation. I from 1 to n and j from 1 to m. Let's see, ij, ai and bj. So what does this mean? So this means j runs from 1 to m, I runs from 1 to n. And we just add these terms, ai and bj. So this would be, so first let's move j. Okay, fixing I as it is, we change the values of j from 1 to m. So that would be b1, ai, b2, ai times bj. So but j moves from 1 to m. So b3 and so on, and ai bm. So this would be it. Then we change, move I from 1 to n. So from this one, I is 1, b1, and so I is 1 and b is 2. I is 1, b is 3, and so on, and I is 1 and b is m. Then I is moved to 2, and so on. And in the end, we should have I equal to n. So this double summation results in this summation. So this is the double summation. And as you can see, we can actually factorize a1 from this first row. So that would be a1, b1 plus b2 plus b3 plus and so on, and bm. And for the second, for the second line, we can factor A2 out, right? Every term in the second row contains A2. So that would be A2 times, so B1, B2, B3, up to Bm. So this can continue up to the last line, that where we can factorize An out. But however, look at this. This is equal to sum of bj's, right? So this is also equal to this. This is also equal to this. So we have A1 and sum, and A2 and sum, and An and sum. Okay, but this summation, this is just a number. Okay, this summation as a whole is just a number, and we have the same number here, here, and here. So we can factorize this number out, and after all, we have A1 plus A2 plus An. So we factor this summation out. We have this. But look at this. This is nothing but summation of A from 1 to n. Right? So this part becomes this, but we have also this. So, after all, we have this. So we started from here to arrive here. So let's summarize the result. For this double summation, AI Bj, this is actually equal to AI Bj.